menyerah, bangkit semula, terbang menuju.
This is our model. For our model called satellite dish, we use three main materials. First, for the construction side, we use cardboard. Second, for the body part or the mast, we use inside the mast we use stick and cover it up with aluminum foil to make it more stronger. And for the satellite dish itself, we use aluminum foil and shape the aluminum foil like parabola.
So for the introduction, satellite antennas or parabolic dishes are one of the best real-life applications of parabolic geometry. They are designed using the mathematical properties of a parabola, which help them collect and concentrate the radio wave efficiently. So the main idea is simple but powerful. The parabolic shape ensures that all incoming parallel signals are reflected to a single point called as focus. These properties allow antenna to receive weak signals satellites thousands of kilometers away in space. So the secondly is structure of parabolic antenna. The typical satellite dish is a three-dimensional parabola, also known as a paraboloid. It is shaped just like a parabola, rotate around its axis of symmetry. Its important parts of the antenna correspond to parts of a parabola. The first one is vertex. Vertex is the center or lowest point of the dish. The second one is focus, the point where all reflected radio wave meet. This is where the receiver, which is we call L and B, is placed. And the third one is directrix, a theoretical line opposite the focus that helps define the curvature of the parabola. So, axis of symmetry, the line passing through both the vertex and the focus. So, the third one is mathematical concept. In analytical geometry, a parabola is defined as the locus of all points that are the equidistant from the focus and the directrix. The standard equation of a parabola that opens upward is y equal to ax squared. So here, the focus is located at 0, 0 and 1 over 4a. So the directrix is the line y equal to negative 1 over 4a. So the vertex is at the origin, which is 0, 0. So this relationship control the depth and width of a parabolic shape. In satellite antennas, engineers use this same equation to design dishes that perfectly reflect signals to the receiver. Alright.
When radio waves from a satellite reach the Earth, they are almost parallel because the satellite is very far away. When these waves hit the parabolic surface of the antenna, each wave reflects according to the law of reflection. The angle of incidence equals the angle of reflection. Because of the parabolic shape, all reflected rays converge at the focus. The LNB, low noise block receiver, which is placed at the focus, collects all these concentrated signals. These signals are then sent to the decoder or TV for processing. Thus, the parabolic reflector acts like a magnifying mirror for radio waves, increasing signal strength and clarity.
Okay, let's take a look on the question about analytic geometry. Let's read the question together. A hyperbola has its center at the origin and transverse axis along the x-axis. The vertices are at 5 to 0, negative 5 to 0, and the foci at 34 to 0, and negative 34 to 0. The first equation states, write the equation of a hyperbola. So, we know that the equation of hyperbola is x squared over s squared minus y squared over b squared equal to 1. So, the equation has already given the vertices, so we write down these vertices. So we need to find the value of a squared. So we write the a squared, we write the a equal to 5, and we transfer the square root into a. So we get the a squared equal to 25. Therefore k is equal to 34 to 0 and negative 34 to 0. So we need to find the value of c squared. So we write c equal to 34 and we transfer the square root into c. So we get the c squared equal to 34. We haven't done yet. We need to substitute this value into this equation. We need to find the b squared because the equation of hyperbola has a b squared. So substitute the value 34 minus 25. So we get the b squared equal to 9. So we insert this a squared value and b squared value into this hyperbola equation. So our final answer is as x squared over 25 minus y squared over 9 equal to 1. So that's it. Alright, second question is find the equation of the asymptotes. You know that the equation of asymptotes is y equal to plus minus a over bx. So we need to find the value of a and b. So the value of a squared is 25. So transfer the power of 2 to 25. So we get the a equal to 5. So we need to find the value of b. So b squared equal to 9. So transfer the power of 2 to 9. So we get the b equal to 3. We haven't done yet. We need to insert the value of a and b into this equation. So we insert the 5 into a and b into 3. So this is our final answer, which is y equal to 5 over 3x or y equal to negative 5 over 3x. So that's it. Alright, so question 3 say determine whether the point 7, 3 lies inside, outside or on the hyperbola. So the point is 7, 3. So we need to substitute this value into the hyperbola equation that we already obtained in question 1. After we substitute like this, we solve the equation and we get the 0.96. When we get the 0.96, so we compare to 1. So 0.96 is less than 1. What does it mean? This means the point is inside the hyperbola, which is in region between the two branches. So our final answer is since if 0.96 less than 1, the point seven is so that is our final answer.